So Parth Nikra is going to present adversarial reprogramming of text classification neural networks.
Everyone, I'm Parth, and I'll be presenting this work, which was done as a joint work at UCSD. And the gist of this paper is that we're trying to reuse neural networks for alternate tasks, more specifically text classification neural networks. And one of the motivations behind this work is that neural networks are being deployed in various real-world settings these days, or will be deployed in the future, like autonomous cars, voice assistants on the smartphones, machine translation systems, etc. So it's really important to ensure the safe deployment of these models in various real-world settings. And to ensure the safe deployment, we need to study what kind of vulnerabilities exist in these systems. So one of the more commonly explored vulnerability in the past few years is something called adversarial examples, where an attacker or an adversary slightly modifies the input so that the new input looks very similar to the original one to the human eye, but it can completely throw off a machine learning model. For example, in this case, an image of a cat is very slightly modified by adding a small noise to it, so that the resulting image still looks like a cat, but a machine learning model is classifying it as guacamole with very high confidence. So such things can be a little dangerous, so it's important to ensure what kind of defenses can be developed to prevent this. And another class of attacks, which is a little more ambitious in its intent, is something called adversarial reprogramming. And the question which adversarial reprogramming tries to answer is that can we repurpose a machine learning classifier for an alternate task for which it was not initially trained for? For example, if we have an image model which classifies animals into various categories, can we repurpose it for classifying handwritten digits instead? And when we think about this question, it reminds us of a very similar objective of some other task, which is called transfer learning, where we try to do exactly the thing which I just described. So if we have an original image classification model that's classifying animals into various categories, if we want to repurpose such a network for, let's say, classifying handwritten digits, what we would do is that we will retrain the last few layers. So we'll change them, we'll map it to our new set of classes, and then we'll retrain just that part of the neural network to achieve this adversarial goal. So right now it's not adversarial, sorry about that, but essentially what's happening here is that the remaining part of the neural network acts as a feature extractor, and we're just retraining a part of it so that we can achieve this new task. Now, adversarial reprogramming is trying to do something very similar, but something slightly different. And the thing is that we're trying to not change anything in our neural network for doing the adversarial task. So now what we're trying to do is that can we keep the network fixed and still use it for, let's say, classifying handwritten digits? And the way we do this is a work by Elsa and others at ICLR 2019. And the way this is done is that we first define a label remapping between the two tasks. So we say that, okay, we'll interpret a label dog as 5, a label cat as 4, a label lion as 0, and so on. And given this label remapping, can we learn an input transformation, which will be universal across all our inputs, and so that we achieve this adversarial task? So we would like to modify all images that look like 5 into an image that gets classified as a dog, so that we interpret it as 5 eventually. And interestingly, what has been shown in this work is that this adversarial program can be something as simple as an additive contribution to all your images. So we can train like a universal noise, which can be added to all our inputs so that we can repurpose our original model for classifying digits. So instead of learning a whole new network, now we're just learning one universal noise, which can be added to every image so that we achieve this adversarial goal. So now the question is that, okay, how is this adversarial, or how is this even an attack? We are just repurposing a network for an alternate task. But the thing is that if we can repurpose a network without changing anything in it, it potentially means that we can repurpose a publicly exposed machine learning API for an alternate task. For example, if there's a Google language detection API, we can potentially repurpose it for something like DNA sequence classification. Or we can repurpose it for tasks which may violate the code of ethics of the system provider, and that's something which is not desirable. So the next question is that what are the challenges in the existing approaches for adversarial reprogramming, or what has been done and what needs to be done? So currently, like before our work, adversarial reprogramming has only been explored in continuous input spaces like that of images. So the adversarial program is an additive contribution, so it can only be applied to input spaces that are continuous and cannot directly be applied to input spaces which are discrete, like that of text or sequences. Similar, and also another thing is that adversarial reprogramming has only been studied in a white box setting, where it is assumed that the attacker has access to the model parameters and architecture, which might not be a realistic assumption to make in a practical setting. So we're trying to address these two questions in our work, and coming to what we are trying to do, this is our goal, that we have a victim model that's trained for some text classification tasks. For example, we have this victim model that's classifying questions into various categories, that whether this question is an abstract question, or is this a question about a human, or is it about a location or an entity. And we want to repurpose it for classifying ethnicities of names, let's say. So we want to classify a name Enrique as Portuguese, using our original victim model, which was trained for classifying questions. And the way we would do this, like giving a high-level picture of that, is that we'll again start with a label remapping function, where we'll say that label human will be interpreted as Portuguese, a label entity might be interpreted as Spanish, and so on. And given that label remapping, can we learn this adversarial reprogramming function at the bottom, which can transform a sequence of characters into a sequence of tokens, which is words that can be accepted by the victim model, so that we can classify the name Enrique correctly, again, subject to our label remapping function. So now our goal here is to learn this adversarial reprogramming function. And before we dive into that, let's just see that what are some desirable properties of this reprogramming function. So one of the important considerations is that this reprogramming function should be something that's computationally inexpensive. Because if it's something that requires like a lot of resources, then in the same cost, the attacker might as well just train a new classifier instead of repurposing some victim model for this task. And secondly, it should be powerful enough to do adversarial reprogramming. So for example, a very simple choice for the reprogramming function would be a simple vocabulary remapper, where we say that an H can be mapped to other, E can be mapped to always, N can be mapped to live or live. And we show in our experiments that that might be too simple to do adversarial reprogramming. So what we instead propose is something what we call a context-based reprogramming function, where if we want to map a token T3 to, let's say, a token S3 in our original vocabulary, what we do is we look at the surrounding context of T and then generate a probability distribution over our original vocabulary, and then sample a token from it. So it's looking at a context, and it's predicting a token in our original vocabulary. And the way this is implemented in our program is by a single 1D convolution layer with filter width equal to the context size. And what you can think right now is that when you want to use it finally in production, or when the attacker is actually attacking using this, you can implement it simply as a lookup table, where you're looking at a set of K tokens and then predicting a token from your original vocabulary. So the next thing is, OK, once we have this reprogramming function, how do we train it? How do we use it? So the whole setup looks something like this, that our sequence T goes through this reprogramming function, gives us a sequence S, which goes through the original classifier, and it gives us a label ls, which goes through our label remapping function, and gives us the final label lt. And if we have a data set of T and LT, which is our adversarial data set, how can we learn this reprogramming function? Now, we can think of it as a neural network, and we want to backpropagate all the way through the network to train the reprogramming function. But there's one slight problem here, which is the sampling step, and that is non-differentiable. So we propose our attack in two attack scenarios. One is the white box attack setting, where instead of passing the sample sequence, we are passing the Gumbel softmax distribution to the victim classification model, which makes this whole setup differentiable. A Gumbel softmax distribution is just a modified softmax distribution, which is parameterized by a temperature parameter, which controls how skewed the distribution would be. And we anneal the temperature parameter during training to train the setup. And this is a white box setting, so we are assuming that we can backpropagate through the classifier C. Now, we also propose the attack in the more challenging black box setting where it's assumed that we cannot backpropagate through the classifier C. So we simply query it for the label, and based on the prediction, whether it's right or wrong, we get a reward. And based on the reward, we train our adversarial reprogramming function using the reinforce algorithm. Now, I'll just move on to the results because I'm running short on time. So these are some of the data sets and models which we'll try to attack. So we have some victim models, which are LSTMs, bi-LSTMs, and 1D CNN-based networks, which were trained on these data sets. The first one is names. The second one is questions, the one I talked about in the examples. And then we also have some real-world data sets like Arabic tweets and IMDb sentiment classification data sets. And these are just some examples of the adversarial sequences. So for example, a name, RYOO, gets transformed into a sequence of words, which gets classified as an entity, which is mapped to Korean and achieves the correct class. The correct predictions are shown in green. The wrong prediction are shown in red. So what you can see here, like the gist of the slide, is that this adversarial sequence does not really make any sense to a human, but to a classifier, it's being mapped to a class which the adversary wants, or which the adversary made it do. And these are some of the results, and I'll highlight a few of them. One is, so if we are repurposing an LSTM network that was trained for IMDb sentiment classification for a task like classifying the sentiments of Arabic tweets, we are able to achieve 88.25% accuracy in the white box setting. And if you train a model from scratch for Arabic tweets classification, the best accuracy you will get is 88.75. So you can see in the white box setting, we are able to achieve accuracies which are very close to what you would get if you train a model from scratch. And very interestingly, what we observed is that if we are doing this white box attack on a random network, which was untrained, the accuracies we get are a lot worse than the accuracies we get on attacking a trained model. And another experiment which we conducted was this effect of context size. So as I explained, that if we use a very simple reprogramming function, which is just a simple vocabulary mapping where the context size is 1, we don't get good accuracy. So it makes sense to use a larger context size. And for our experiments, we used a context size of 5. So this is just the conclusion of our work, which I just went over, that we, for the first time, demonstrated that RNNs can be reprogrammed, and we also proposed adversarial reprogramming in the black box setting. And our code is publicly available on GitHub, and I'll be happy to take questions. Thank you.
We have time for one or two questions.
Hi, thanks for a great talk. What would you do if your victim model's output space is smaller than the output space you're trying to predict?
Yes, that's one of the details I did not mention. So we are assuming that the number of labels in our original task are more than the number of labels in the adversarial task. If that's not the case, we might have to come up with a different solution, but I'm not really sure about that. But this is the attack scenario that was also proposed in the work on images, so we kind of just extended that idea and assumed a very simple label remapping. But thanks for that question. Yeah. Yeah.
Hi, thanks for the talk.
Yeah.
So did you also sort of figure out what tasks can be compatible as victim and adversarial? So I know you gave us a few examples.
Yeah.
But do you have any sort of intuition or study on what sort of tasks, either quantitatively or qualitatively, go well together in some manner or form?
Yeah, that's a good question. Like intuitively, one of the main intuitions I have is that the adversarial task should be something that's simpler to do than the original task. For example, in our case study, the adversarial task, the sequence length wasn't very big. So we are not very sure how good it will perform if our adversarial sequences are longer. But since this was one of the first works done in this area, we did not really try those experiments out. yet, and also seeing the work on images, the adversarial tasks which were chosen were slightly easier, like digit classification or Cipher-10 image classification. So, yeah, thanks.
Okay, let's thank the speaker again.